Well, this first part of Module 10 is fairly long, and I'm uh, just going to concentrate on a couple of key points from the reading and the slides in this video. So the first thing we're looking at is what is the history of the Earth's temperature? So I'm going to show a lot of slides that have some curves that are showing data that are showing the history of the Earth's temperature. We're going to remind ourselves how we measure the temperatures in the past before there were people out all over the planet using thermometers. But we'll start off with just the last 150, 170 years or so with relatively modern temperature measurements. And of course, the accuracy of those measurements has gotten better in the more recent time. And you can see that from the last half of the 19th century, there wasn't a clear increase in temperature. First half of the 20th century, it increased, then it was constant for a couple of decades, and then it's been increasing quite dramatically. And you can remember in the carbon cycle that the rate of carbon going into the atmosphere has been increasing. So it is not surprising that we would see a change in the rate of the response of the system to the planet as it loses the ability to respond to the ever increasing forcing that it's getting from carbon. Um, this figure is just to illustrate that different groups measure the temperature and account for, you measure a temperature at a certain location, then you try to turn that into a global average. And so there's some modeling that's involved in turning that into global averages. So this is just showing three different groups uh, and their differences of a tenth or 2/10 of a degree between them. Those are what we call systematic offsets, but the trends are consistent between them, and even the small scale fluctuations from year to year are quite consistent between them. This map is a little bit scary, but it shows the temperature change compared to the sort of second I guess the latter part of the 20th century. So just in the last 25 to 30 years or so, the temperature change, the darker colors indicate a bigger temperature change, and the biggest temperature changes are in the northern hemisphere over land where people live, but especially in the Arctic Ocean. And one reason for that is as you're putting more energy in your the system wants to distribute things evenly. And so that means wiping out or diminishing the temperature gradient between the warm equator and the cold poles. As an extreme example, we can go back to our comparison with the other two terrestrial planets, Venus and Mars. Venus has a very extreme greenhouse effect. And even though it rotates very, very slowly, it takes it almost a year to rotate. That means its day is very slow. So on the night side of Venus, you're on the opposite side of the planet from the sun for over 200 Earth days. The temperature on that night side is the same as on the day side. The greenhouse effect is so big that you trap all that energy and the planet redistributes it perfectly evenly. So as we increase the forcing, the warming on the planet, you see a greater change in that temperature in the cold places where it's easier to warm things up and to diminish the difference between the warm spots and the cold spots. You also notice here that there are some regional irregularities. There's a part of the North Atlantic that's actually gotten a little bit cooler, and that has to do with disruption of ocean currents. Speaking of ocean currents, this figure on the lower left shows the amount of energy stored in the oceans as thermal energy. We've talked about thermal energy as one of our forms of energy. It's just the kinetic energy of the atoms and molecules in a substance. So the oceans have thermal energy. And in fact, this thermal energy, the fact that the oceans have increased their heat content by 10 to the 23 joules compared to what it was in 1990, for example. All that extra energy has is thermal energy of the oceans. That by itself has caused the oceans to expand. When you heat things up, generally they expand, and the oceans are no exception. So part of the sea level rise that we see currently is not due to melting. Some of it's due to melting. Some of it is just due to the fact that the oceans are warmer and have expanded. And that's actually gives some several centimeters of sea level rise. We've spent some time on this slide in the previous section, so I won't talk about that. This is the next important thing for this part. What is leading to the temperature increase? How can we be sure that it is the greenhouse effect and not something else going on with the sun? We previously looked at the magnitudes of the forcings, and we know that the energy magnitude of the greenhouse gas forcing is much larger than variations in the sun. But this is another direct piece of evidence that shows that it is the greenhouse effect. Back in chapter 12, we looked at this simple model of the Earth's energy flow, a simplified version of what you see in the lower right-hand corner of this slide, where there's just the energy into and out of the surface and the energy into and out of the atmosphere. And the temperatures here show that the surface and the lower atmosphere have gotten warmer, but the stratosphere, which is the layer above the troposphere in the atmosphere, has gotten cooler. That is a very strong piece of evidence that shows that it is, in fact, the greenhouse effect that's warming the planet. And here's why. Greenhouse gases in the stratosphere absorb infrared radiation and prevent it from getting out into space. But ultimately, the total amount of energy getting from the planet out into space has to balance the energy coming in from the sun. So if the atmosphere is blocking the energy coming out by absorbing that infrared radiation, then I've got to have a greater output of energy from the surface. And that means I'm going to have an increase in the temperatures at the bottom of the atmosphere and at the surface, but a decrease in temperatures in the upper part of the atmosphere because they are radiating less while the surface radiates more in order for that to balance out. So just to say it again, if the greenhouse gases are absorbing radiation, but I still have to get the same amount out, the only way to do that is to pump up the surface temperature. If I pump up the surface temperature, I will see a decrease in the radiation to space from the stratosphere, which means a lower temperature in the stratosphere. The next few slides are just showing various instrumental records going back various distances in time of what the historical temperature has been. This one goes back 1,000 years. This one goes back a few million years. This one goes back 1,000 years again. And you can see that there are fluctuations in the temperature on these various time scales, and we now have a sharp and sudden increase in the modern time scale. Based on geologic studies, we also have evidence that the Earth is warming based on the extent of ice. So in the last ice age, we had ice sheets extending all over Canada and well into what is now the United States. And we're seeing these ice sheets retreat. This shows what it was like 18,000 years ago, up to the end of the last ice age about 8,000 years ago. And when the ice melted, temperatures are much warmer. As a reminder, how do we get those past temperatures? We get them from ice cores. We drill down. Each year, there's a new band that helps us count how far back in time we are going. We saw this slide in a previous module. And by analyzing the trapped air bubbles and the isotopic abundances in those air bubbles, we can measure the temperature as well as the composition of the atmosphere back in time. By doing that, we see some interesting things. This is one particular example where the temperature of the Earth rose, the global temperature of the Earth rose 10 degrees. That's 10 degrees C or 10 Kelvin, 16 degrees Fahrenheit, over a time period as short as 300 years. That's this sudden spike that you see just after this cold period called the Younger Dryas event. And so the Earth's temperature is more like the ocean motion. The Earth's climate's more like the ocean motion than the stable stella. it can change very suddenly by very large amounts. The warm times that we've been enjoying for uh, modern human civilization are unusual. This is looking back at temperatures for 150,000 years, and you can see that that is dominated by ice age conditions with relatively short of a few thousand years um, interglacial periods, which is what we're currently living in. And the current interglacial period has actually been very stable, unusually stable compared to previous systems. And so when I was a student, I was really worried that we would plunge back into an ice age. Now we're looking at going in the other direction. Now we take that same temperature curve and take a look at what was the carbon dioxide abundance in the atmosphere, and you can see that they track very closely. When the CO2 is high, the temperature is high. When the CO2 is low, the temperature is low. Now we're looking at the CO2 going up. This curve is stopping at the um, time of the Industrial Revolution, but now the CO2, remember, is up over 400 on this scale that is only going up to 300. Looking back a little bit further, and now time is going in the opposite direction here, so the present is at the left, the past is in the right, and you can see a number of these ice ages. Every place this black curve is down low, where that dash line is, those are ice ages, and it's only those narrow spikes, number 5, 7, 9, 11, that you see there. Those are the interglacial periods that are relatively warm and pleasant. But here again, we see the point of this slide is that the carbon dioxide abundance in the atmosphere tracks very closely with the temperature. So we have very strong evidence over hundreds of thousands of years that when CO2 is high, the temperature is high. And this slide tracks back even further, 500 million years. And of course, as we go further back in time, we don't have as fine a resolution year to year, and we have greater uncertainties in the temperature measurements because we're using different techniques and we don't have as much data to get those temperatures. But we see that there are these large variations in temperature, including temperatures that are several degrees warmer than what we're currently experiencing, which is just to illustrate that it is possible for the Earth to be much, much warmer than it currently is. And finally, one of the natural forcings that we sort of alluded to was solar output. There's another natural forcing that has to do with little changes in the Earth's orbit and the Earth's spin. So those are called Milankovitch cycles. There are 3 Milankovitch cycles. They have to do with the shape of the Earth's orbit, how egg-shaped it is. That's this term called eccentricity. The tilt of the Earth's spin axis, that's currently 23.5 degrees, and it's how much the North Pole points towards the sun in the summer and how much it points away from it in the winter. And then there's a wobbling of that axis as well. And all of those things result in little different inputs of solar energy to the Earth. And we can actually see those when we look at the temperature measurements that we use going back in time with the uh, uh, variations in isotopic abundances of oxygen, those air bubbles. This is going back 3 million years. And a lot of these little small scale bumps and wiggles are due to those changes, those Milankovitch cycles, those changes in the Earth's spin and its orbit parameters. So again, I make the analogy to the ocean motion and the stable stella from the beginning of the semester. If you've got a system that is susceptible to changing dramatically when there's a perturbation, that's the kind of system that you want to be very, very careful about making a big change to. And so the magnitude of the forcings that lead to these Milankovitch cycles is smaller than the current magnitude of the forcing that we are doing by pumping greater and greater amounts of carbon dioxide into the atmosphere. So here is, by analogy, a planet that has capsized many, many times in the past or its history due to much smaller perturbations than the perturbation that is currently happening due to changes in the greenhouse abundance in the atmosphere.